All right, now we're going to go into section 2, and we have our two learning goals that we're actually going to look at here, which are 4.03. I can use Coulomb's law to illustrate the electron repulsion energy, and I can predict bonding types based on atomic properties. Now, we're going to go through this part of the unit. It's got a few more things that are going to be introduced in there. Um, it also is going to introduce a little bit of the idea of what's going on with intermolecular forces. So just work with it as we go through, and I will try my best to make sure that everything makes sense. So if it does not make sense, please, please, please make sure you take the time and see me in class, and we can get those things handled. Now, as you see at the bottom of each slide, you're going to see exactly which section or chapter and section in the textbook it was pulled from. That way you can use it as a reference to go back and look over a few things. Chemical bonding. Now, what is chemical bonding in the first place? It's chemical bonds holding atoms together. Either sharing of electrons or using information we have from our previous periodic trends. We're actually going to be able to predict a lot of the different types of chemical bonds that are going to be formed. Now, there are three main types of chemical bonds. First, ionic, which are going to be held together by electrostatic forces. Remember that positive and negative charge? That's going to be what actually holds them together. We have covalent bonds, which are going to result from sharing electrons, and we have metallic bonds. Now, we're not going to spend much time talking about metallic bonds here. We're going to mainly focus on ionic and covalent. Now, when we talk about bonding, we have to pay attention to the valence electrons, or the outermost electrons. And this is usually going to be demonstrated as you see where we use our Lewis structures, which are given to you here in this table, in both these columns. And it's just basically showing the element symbol and how many valence electrons that they have based on their location. This is going to be determined by the group number with the A next to it. So if we look at our periodic table and you see where it says 6A, that's going to tell you that there are 6 valence electrons to worry about. Now, exceptions to this rule. D or F blocks usually have 2 valence electrons, but because of the fact that they have these higher orbitals, they're going to be able to do some things that the other ones will not. So we usually save those for last. And also hydrogen and helium. Helium only has 2 valence electrons, and it's because it's only on the lower level. Now, all of our atoms have the same goal. They want to have a full outer shell. The one that's usually going to be involved in this, we talk about the S and P orbitals. So they want to have a full octet to achieve noble gas configuration. The exception to this is hydrogen only needs 2, because again, helium only can hold 2 valence electrons. Now, as we look at this information, we're going to, later on in the year, we'll talk about electron configuration. We'll talk about how we actually get this noble gas configuration. But the goal is noble gas configuration is lower in energy. So if it has to lose or gain in any electrons or number of electrons, many times these atoms are going to be willing to do this in order to be stable, as what we call it, or in this lower energy level or lower energy amount. Some of the nonmetals can have more or less than 8, and we'll again talk about those exceptions at another time. Now, Coulomb's law. This is going to be talked about in 8.1, but basically this is a law that we're going to, or a formula, sorry, that we're going to use to understand the amount of energy that's used in formation of these atoms, or the interaction, sorry, between these atoms. So we have our constant here, E 2.31 times 10 to the negative 19 joules per nanometer, or times nanometer, times this quantity here, where each of these, Q1 deals with the charge on the first ion, where Q2 is for the second ion, and R is again the radius of the atom. This is going to let us know, based on the distance and the charge we have between these two atoms, where their lowest stable point might be. Now, let's look at this example in this diagram. If I have 2 hydrogen atoms, which is what you're seeing here, at this point they have no interaction. The closer they get together, the more that we actually pull together. But there's a certain point that will be ideal. So you notice that here They're sort of at about a 0 point, and we're noticing that the further they are apart, the closer we get to this 0 level. But here, at approximately 0.074 nanometers, which is given to us here, this is sort of the lowest energy state that we'll find it. This is the ideal situation. Now, what happens if we get too close? Well, we end up getting too close, then we end up losing a little bit because now we get the repulsion. If the nuclei are too close together, positive and positive will repel each other, and so they'll push themselves apart. This distance here, this 0.074 nanometers, gives us exactly, or approximately, sorry, negative 458 joules of energy, kilojoules per mole. This is going to be the most stable point for our hydrogen, and the other reason why, as we'll see later on, it usually forms into a diatomic. It's much more stable paired this way than it is if it's out on its own. So, moving forward, talking a little bit more about the different types of bonds. Now, metallic bonds we always look at as a sea of valence electrons, but again, not so crucial right now. It's talking about the fact that the electrons from each of the atoms will be what we call delocalized, or they're able to move around between atoms. For covalent bonds, we're talking about the sharing of those valence electrons, and ionic, dealing with transferring the electrons, not just sharing them, but actually giving them over and allowing them to be at a lower state. Now, ionic bonds are usually going to form between an element of low ionization energy and one of high electron affinity, hence the thing that we're looking at here. Once we pull away that electron from the lower, which is going to usually be our metal, it's going to be attached or given to the one that has the higher electron affinity, usually our non-metal. Now, specifically covalent bonds, atoms share the electron in their valence shell, usually between two non-metals. If you're looking at what we have here, we have chlorine, which has 7 valence electrons. In order to be stable or have the lower energy, it's going to bond with another chlorine. So we have Cl plus Cl. It's going to give us this type of bond. Now, these electrons are still going to be held onto by both of these atoms, and they can be broken with sufficient energy being added. We're going to see the same type of situation as we look through all of our covalent bonds. Now, one way that you'll see them represented, just in case you don't see it as a dot, is you'll see a nice little line. That represents a covalent bond, or electrons being shared between them. Now, there can also be multiple covalent bonds shared. Double, single, and triple bonds, letting you know how many pairs of electrons will be being shared. But we're moving along just a little bit. Now, into the bond lengths and bond strengths. Single bonds are going to be the longest and the weakest of the bonds, meaning it doesn't take as much energy to break those types of bonds. But the more that we add, being double bonds is going to get a little bit stronger and a little bit shorter. Triple bonds, very, very close together and going to be very, very strong, or you have to put a lot of energy in to break those types of bonds. Why is this going to be important? As we move towards understanding the energy relationship in our reaction, we have to look at how much energy do I have to put in to break each of those bonds. Single bonds is going to be much easier, of course, whereas our triple bonds are going to be much more difficult and require a lot more work, usually resulting in a higher delta H for our reaction, or change in enthalpy. Now, bond polarity and electronegativity. This is the point we're trying to actually move towards, and I want to look at a couple of things. This is going to tell us what type of bond is going to form and what to basically prepare for. Now, electronegativity is actually going to describe an atom's attraction to an electron pair in a bond. So this is more of a tug of war. We don't think of it as it's trying to steal the electron, but it's actually which element is stronger and is going to win out in the tug of war and pull that electron closer. The difference in electron and electronegativity size indicate whether it will be polar, nonpolar, or ionic. If we have one that has a very, very low electronegativity, one that has a very, very strong, it's not going to be able to hold on to the electron. It's actually going to transfer it completely away. Now, between each of these types, you notice that I have 0.4 here at the bottom, or 0 to 0.4, 0.4 to 2.0, 2.0 to 4.0. Each of these values is not necessarily a hard boundary. So I wouldn't say 0.5 to 1.9 or anything like that. We also have to look at those other periodic trends, look at the electron affinity, look at the ionization energy, and see how that will play into the idea of which type of bond we're going to form. Now, usually if we look at our values, we can tell very quickly whether it be polar, nonpolar, or ionic. In general, this is the pattern that we're actually going to use in order to move forward with this. Now, for electronegativity, again, this is a trend. So we want to talk about what happens as we go left to right and within the group. Looking at our diagram that we have here, you notice that as we go down within the group, that is going to decrease. So higher values at the top and lower values there at the bottom. And it's going to also increase as we go left to right. Again, this makes perfect sense because our metals here are going to want to give away those electrons. They don't want to hold on to them, so they're going to have very, very low values. Whereas our nonmetals want to gain those electrons. They're almost there until they just need to hold on to it a little bit longer, or hold on a little bit tighter to those electrons, or gather more electrons. So they're going to have very, very high values. Our most electronegative element that we're going to deal with here is fluorine. So this is going to be our sort of our guide of how we're going to compare everything else to. This will also explain why in acid-base reactions, why even though hydrofluoric acid is a weak acid, why it's going to hold on to that electron and not dissociate with the others that are also halogens. But we'll get to that in a little bit. Now, knowing this about the electronegativity, this is going to force us to start looking into bond polarity. Because if we have a compound that is a polar covalent bond, we need to look at how the electrons are actually being shared and what's happening between them. Now, we have three possible things that might be happening. We have nonpolar covalent, where we have this equal sharing, which is what we see here with our fluorine gas. We have polar covalent, where it's sharing unevenly, and it's going to cause for a little bit of a slightly positive, slightly negative. That's what this symbol means, slightly. Charge on each of the ions. And we have what's called ionic, which is going to be the complete transfer of the electron from, say, lithium on this side to our fluorine. Also, note the little symbols that are given to you here. It's just showing you which side the electron's being pulled closer to. Now, a molecule that has one side slightly positive and one slightly negative is said to be a dipole. Dipole, di meaning two, pole meaning of our different charges. So we have two sides with different charges. The slightly positive end is going to be represented by lowercase delta here, and the slightly negative lowercase delta here with a negative symbol. And the arrow can also show. Now, how do we know that something is polar? Well, if we have this compound, which in this case this could be sort of like our hydrochloric acid, has a slightly negative and slightly positive end to it. Now, if we put this in a charged system, notice we have our charged plate here, you notice that all the molecules begin to, this hydrofluoric acid, all the particles begin to line up a certain way, with the slightly positive ends towards the negative side and the slightly negative ends towards the positively charged plate. This is going to help us to understand what's happening now, because we have this slightly polar, this polar molecule is going to actually be attracted to the opposite charge. This is going to help us to understand how things are dissolved. This is going to help us to see how things break down, and also why it's easier for some compounds to break down than others. Now, this is where we want to actually end this video and give you a little time to recap and bring everything back and keep it fresh in your mind. Come into the next video, we're going to talk about intermolecular forces. And again, all this is leading us to the point where we look at how energy in reactions actually goes about, or how we find out how much energy is needed for a total reaction. So we're going to keep going from this, and I will see you